So, we are discussing about the transition amplitude from some initial state I to some final state f, which is also given by f in s I in, and what we would like to do is we would like to consider this transition amplitude and express it in terms of the n point correlation functions. So, this is what we have been trying to do. What we did is we considered a initial state which is having momentum q1 to some ql, let us say, and what is the transition amplitude for this state going to some state which is p1 to pn out. This is what we are working, and we would like to obtain a reduction formula for this. So, to do this, what we did is we started with this in state, and then we have seen that we can write this as T1 some A in dagger of Q1 acting on Q2 up to QL in. So, this is a L minus 1 particle state. This creation operator will give us an L particle state which is given by this. We started with this, and since A n dagger is the creation operator for a free field, we can use this formula which is given by A in for free fields. A in dagger Q1 is given by one over I e to the power minus I Q1 dot x times del 0 phi in of x minus del 0 e to the power minus I Q1 dot x times phi in of x. Or we will use this notation such that this is given by 1 over I del 0 acting both the ways e to the power minus I q1 dot x phi in of x. This is what is the expression for A dagger in of q1. We will substitute this expression here, and when we substitute this, what we get is P1 with an integration over d cube x 1 over I e to the power minus I q1 dot x del 0 phi in of x Now, notice that this is time independent. So, this expression here also, when you carry out the integration, it will turn out to be time independent. So, although in other words, here in this expression both e to the power I q1 dot x and phi in of x, both of these are time dependent, but ultimately when you carry out this integration, you will get a dagger in of q1 which is independent of time. So, because of this you can evaluate this integration at any given time. So, this is evaluated at any arbitrary time, especially you can evaluate this integration in the limit t goes to minus infinity or in the limit x 0 goes to minus infinity. So, let us see what we will get. This is equal to dqx 1 over I e to the power minus I q1 dot x del 0 this quantity itself is equal to the same quantity in the limit x 0 tends to minus infinity, but in the limit x 0 tends to minus infinity, the interacting field phi of x is equal to z to the power half phi in of x. So, therefore, in this limit I can substitute this relation here, and in place of phi in of x I can write the interacting field phi of x. So, when I do that, what I get is the transition amplitude is given by limit x 0 tends to minus infinity z to the power minus half integration d cube x e to the power minus I q1 dot x del 0 p1 out and phi of x instead of phi in of x q2 in. So, this is what we have got. Now, what we will do is we will use this relation that if you consider any arbitrary function f of t and you take this object limit t tends to infinity f of t minus limit t tends to minus infinity f of t, then this quantity is nothing but integration dt del f over del t for any arbitrary function of time, where the integration is carried out from some t I to t f in the limit t I tends to minus infinity, t f tends to plus infinity. Okay. So, we will use this relation here. Remember, although this quantity here is independent of time, when you replace phi in of x by phi of x, this quantity need not be independent of time. So, only in the limit x 0 tends to minus infinity, this is time independent and this becomes equal to the other quantity. Alright. So, now what we will do is that we will consider the same quantity and then we will consider it at x 0 tends to plus infinity and x 0 tends to minus infinity. We will take the difference and the difference now will be equal to limit x 0 tends to infinity z to the power minus half d cube x e to the power minus I q1 dot x del 0 p1 out phi of x q2 in minus the same quantity in the limit x 0 tends to minus infinity z to the power minus half d cube x e to the power minus I q1 dot x del 0 p1 right. This quantity now will be equal to integration. Here now integration dt d cube x, where t ranges from minus infinity to plus infinity, and so is x, is just integration over d4 x. Del over del t is simply del 0. Now f of t is just equal to this quantity. So del 0 acting on e to the power minus I q1 dot x del 0 p1 out phi of x q2 ql in. So therefore, this quantity, the transition amplitude here, will now be equal to this quantity minus this quantity. Okay. This minus this will give you this, which is nothing but the transition amplitude. So I guess I missed a 1 over I factor somewhere. In the first step itself, there is 1 over I, and so is it. Okay. The transition amplitude, it is P1 Pn out Q1 up to Ql in. This is equal to this quantity limit x 0 tends to infinity z to the power minus half 1 over I d cube x e to the power minus I q1 dot x del 0 p1 up to out phi of x in minus this quantity here. So minus and 1 over I will make me plus I, and also there is a z to the power minus half. So what I will get here is this plus I z to the power minus half integration d4 x del 0 let me call this variable as x1 in this integration. It is just a dummy variable. So, I can change x to x1. So, this is integration over x1 e to the power minus I q1 dot x1 del 0 p1 up to pn out phi of x q2 up to ql in. Now, let us concentrate on the first term first. In the first term, you take the limit x0 tends to plus infinity. So, therefore, again you can consider this integration here, and this will give you a dagger out q1, right. So, therefore, the first term of the right hand side is simply equal to P1 up to Pn out a dagger out of Q1 Q2 up to QL in. So, what we started is, we started with the transition amplitude, which is equal to the same quantity with this creation of operator acting on the in state, and then we have used this technique to express it in terms of a dagger out of Q1. Now, a dagger out of Q1 will act on this state here. What will you get when a dagger acts on this? It will annihilate one of these one particle states, one of these momenta. To do that, let us consider the conjugate of this, which is what you get when you consider a state A out of Q1 and you act on a one particle state. Let us say this is some one particle state of momentum P. Will you get simply the vacuum, or you will get something else? You will get some normalization factor and a delta function. Okay, so let's just so even when P1 equal to Q, you have to be a bit careful. So let's do that in a slightly more detail. This is A out Q1. This quantity I can write it as a dagger of P, a dagger out of P, P out, this is P out, acting on the out vacuum. Now, this quantity I can write it as commutator of A out Q1, a dagger out P plus a dagger out P A out Q1 acting on the vacuum. But this quantity will annihilate the vacuum. So, the second term will give you 0. The first term is a seed number. We are using the canonical commutation relation where this is equal to 2 pi cube to P 0 times delta of P minus Q1 times the vacuum state. Now, instead of a one particle state, if you have an n particle state here, what you would get is, so this is now what we saw is this is equal to 2 pi q 2 p 0 delta of p minus q 1 . What we have here is an n particle state. So, if we consider an n particle state and act A out of q 1 on such an n particle state, p 1 to p n out, what we will get is this normalizes this overall factor times an n minus 1 particle state, and since there are n variable n such momentum here, this can act on any of these things. So, you have to sum. So, sum over k runs from 1 to n 2 pi q 2 p k 0 delta of p k minus q 1, and this is p 1 up to p k minus 1 p k. I will put a hat here to indicate that this momentum is absent, p k plus 1 up to p n out. So, what you have here is just the Hermitian conjugate of this quantity. So, now when I substitute it, the first term will become a sum of n terms which contains a delta function times some normalization factor times the amplitude which involves L incoming states, or it involves L minus 1 incoming state and n minus 1 outgoing particles. Okay. So, initially you considered the process for particles which are for a process which involves L incoming particles and n outgoing particles. This is the amplitude for this process, and this amplitude, now what you are showing is that can be expressible in terms of sum of this quantity here, which we will simplify in a moment, and the another quantity which involves the amplitude for a process which has L minus 1 incoming particles and n minus 1 outgoing particles. So, at least one of the particles here, so basically this delta function here says that this will give you a non-zero contribution if and only if one of these L incoming particles go without doing any interaction, it is completely undisturbed. On the other hand, if none of these outgoing momenta here coincide with any of these incoming momenta, then this quantity will give you vanishing contribution. Okay. So, this will not give you any contribution if any of these things do not match with any of these QIs because of the presence of this delta function. I will call such a term as a disconnected term here, in the sense that it essentially describes a process which has one less incoming particle and one less outgoing particle. So, now let us focus on the second term. Basically I z to the power minus half d 4 x 1 del 0 q1 dot x1, then del 0 we will evaluate the time derivatives here explicitly, and when we act del 0 on this state, what we get is, first I will write this in terms of sum of two terms, and then we will act del 0 on it. I z to the power minus half d cube x1 del 0 times e to the power minus I q1 dot x1, then del 0 acting on this term p1 out phi of x q2 in, then minus del 0 acting on e to the power minus I q1 dot x1 will give you minus I q1 0, and then this quantity e to the power minus I q1 dot x times this same thing p1 out phi of x q2 in. Now, I will act del 0 on this as well as on this. When I act del 0 on this, it will give me first one term, which is, let us do it explicitly, I z to the power minus half d cube x1. The first term will give me minus I q1 0 e to the power minus I q1 dot x1 del 0 of p1 phi q2, then what I will get is plus e to the power minus I q1 dot x del 0 square acting on this p1 phi of x q2 in. Then I have the second term. So, what I will get is minus I q0 q1 0 del 0 acting on this will give another factor same to that. So, I will get a square times e to the power minus I q1 dot x1, these are x1 p1 out phi of x q2 up to in, that is first term. Then I will get another term, which is minus I minus of minus I q0 q1 0 e to the power minus I q1 dot x1, then del 0 will act on this state. So, del 0 acting on p1 out phi of x q2 in. Now, you can see the first term here is same as this term apart from this minus sign. So, this will cancel this. What you are left with is this and this. There are these two terms here because there is a minus, and then this will make it plus q10 square. Because of this I square and this minus sign, you will get plus q10 square. Now, you can use this relation q10 square is basically q1 dot q1 plus m square. So, we will substitute this relation here. What you get here is, and I will keep this term which is q1 vector dot itself, and then m square term I will just add here. Okay. So when I do that, what I get here is the second term simply becomes I z to the power minus half times it is d4 x1 integration d4 x1, then e to the power minus I q1 dot x1 del 0 square plus m square, because this will give me 1 m square, this acting on P1 up to Pn out phi of x q2 ql in, that is first term, and then the second term is simply plus q1 dot q1 times e to the power minus I q1 dot x1, this term here P1 up to Pn out phi of x q2 up to ql in. Now, the reason I keep it separate is the following. Because of q1 dot q1, what I can do is I can consider this whole term here. I can write it as del 1 square acting on e to the power minus I q1 dot x1. What I am saying is del 1 square acting on e to the power minus I q1 dot x1 is simply equal to minus q1 dot q1 times e to the power minus I q1 dot x1. So, this quantity here I can substitute it as minus del 1 square. So, instead of q1 dot q1, I can write it here as minus del 1 square acting on this. Now, what you can do is you can make a partial integration twice. The surface term will vanish because at spatial infinity you are considering interaction of localized particles. So therefore, the field here it basically consists of several wave packets which vanishes at spatial infinity. So, when you do a partial integration, you will get a surface term here, and the surface term will vanish because of the fact that you are considering interaction of particles which are localized both in position space as well as in momentum space. So, if you use that, then this simply becomes the same quantity, but this del 1 square acting on this term here. So therefore, this quantity here I can now write it as the same quantity, but this e to the power minus I q1 dot x1 and del 1 square acting on this. Now, I can combine this term and this term. What I will get here is the D'Alembert operator appearing in this term. So what you have seen is the second term here is nothing but when the surface term vanishes, at the end of the day you get this term is equal to I z to the power minus half integration d4 x1 e to the power minus I q1 dot x1 del 1 square I will denote plus m square acting on this state P1 up to Pn out and phi of x q2 up to ql in. All right. Now, what I will do is I will consider this term here and then I will see if I can do further reduction to this one. So, let us consider this term here inside this integration P1 up to Pn out phi of x q2 up to ql in. Now, what I will do is I will pull a P1 factor here from the out state and then I will write it here a dagger out P1. So, this is same as P2 up to Pn out a dagger out of P1 then phi of x q2 up to ql in. Again, because this it is not a dagger, it is simply a, because a acting on this state will create a one particle state. So, this now what I will do is this is a is an annihilation operator again for a free field. So, I can express it in terms of the phi out field. So, therefore, this is integration. I will use y as the variable dqy or y1 because there is a P1 here e to the power I P1 dot y1 times I del y1 0 acting on this P2 up to Pn out phi out of y1, this is x1 here, right, x1 q2 sorry phi of x1 q2 up to ql in. All right. Again, this here is time independent, therefore, I can evaluate it at any arbitrary time, especially I can evaluate it in the limit y1 tends to plus infinity. So, this quantity itself is equal to the same in the limit y1 0 tends to plus infinity, and in this limit what I can do is I can replace this by z to the power minus half times phi of y1 in the limit y1 0 tends to plus infinity, phi y goes to z to the power phi y1 goes to z to the power minus half, z to the plus half phi out y1. So, I can use this relation here, and what I will get here is essentially there is a factor of z to the power minus half and there is no phi out. So, this times z to the power minus half. I will consider this and I will take it out in this integration. Then what I have is the amplitude P1 to Pn out phi of x1 q2 ql in this is equal to limit y1 0 tends to plus infinity I z to the power minus half integration d cube y1 e to the power I p1 dot y1 del y1 0 acting on p2 out phi of y1 phi of x1 q2 in. This is what I get. Now, you see I am taking the limit y1 0 tends to infinity and this operator here is left to this operator. This is at any finite time, and here you are considering the limit where y1 0 tends to infinity. Therefore, this expression here is equal to time order product of itself. So, I can introduce a time ordering here because of this fact, because of the fact that I am considering limit y1 tends to plus infinity. Now, what you do is you consider limit y1 0 tends to minus infinity of the same quantity and you take the difference. So, limit y1 tends to minus infinity of I z to the power minus half d cube y1 e to the power I p1 dot y1 del y1 0 p2 out time order product of phi of y1 phi of x1 q2 in. Now, you see why I wanted to emphasize on the time ordering, because when you consider the limit y1 tends to minus infinity, the time ordering will make sure that this phi of y1 operator goes to the right of phi of x1. So, it is on the right. Now, you can carry out this integration over y1 dq y1. When you carry out the integration over y1, what you get is a of p1 acting on this. So, this will annihilate one of these in states. So, therefore, this here is nothing but integration will go away. This is p2 up to out phi of x1 a in of p1 acting on Q2 in. So, again this will give a disconnected piece. Now, you take the difference of this and this. So, this quantity itself is difference of this and this plus this term here. So, therefore, this is, when I take the difference of this and this, again I will get an integration over d4x. So, limit y1 0 tends to plus infinity I z to the power minus half times the whole quantity minus limit y1 0 tends to minus infinity I z to the power minus half times the whole quantity here is equal to I z to the power minus half integration d4 y1 times del y1 0 acting on the whole thing times e to the power minus I e to the power plus I p1 dot y1 del y1 0 p2 out time ordering of phi of y1 phi of x1 q2 in, right. So, therefore, this quantity here is this plus this. So, let us write it. This is equal to I z to the power minus half d4 y1 del y1 0 e to the power I p1 dot y1 del y1 0 p2 out time order product of phi of y1 phi of x1 q2 in plus this quantity plus p2 out phi of x1 a in of p1 again I can consider this term here and this the first term here can be written as I z to the power minus half d cube y1 e to the power I p1 dot y1 del y1 square plus m square acting on this term p2 out time order product of phi of y1 phi of x1 q2 up to n, right. So, what I can do is I can substitute this result here in this expression then I will get a disconnected term plus so what I will get is I z to the power minus half square d4 x1 d4 y1 e to the power minus I q1 dot x1 plus I p1 dot y1 and then del y1 square plus m square del x1 square plus m square acting on P2 out time order product of phi of y1, phi of x1, q2 up to ql in plus disconnected terms. I can keep on doing this, the same process, and when I do that at the end of the day, what I get is the amplitude for this process where you have n outgoing state, n outgoing particles and L incoming particles with momentum q1 up to ql. The amplitude is given by disconnected terms plus I z to the power minus half to the power L plus n d4 x1 up to d4 xl d4 y1 up to d4 yl yn e to the power minus I q1 dot x1 plus ql dot xl plus I p1 dot y1 plus up to pn dot yn, this times del y1 square plus n square up to del yn square plus m square, then del x1 square plus m square up to del xl square plus m square acting on the vacuum expectation value of time order product of phi of y1 up to phi of yn, phi of x1 up to phi of xl this is what you will get. So to summarize, what you can do is you can consider the S matrix element of some phi, some final state with some initial state. If you evaluate the connected part of the S matrix element, then the connected part is given by this. So, this is what is known as the connected part of the S matrix element, and what you can do is you can consider the outgoing state to be union of So, you can consider various subsets. This is your final state here, this is your incoming state. This incoming state contains n incoming particles. You can consider all possible subsets here, okay? And similarly, you can consider all possible subsets here. You can compute the connected part of the S matrix elements, take their product and take the sum. That will give you the final S matrix element here. So, symbolically what I can write here is, I can write here is, so some alpha union over alpha I and I alpha I union over beta j union over beta j, where alpha I and beta j are basically a subset of the outgoing and a subset of incoming state, or especially this P1 up to Pn, that I can consider it as union of alpha I for various alphas or for various i's, various j's, and same about the incoming state, and then the product over these states with alpha I, the connected part beta j here. Okay.